What is SVD's role in PC, a dimensionality reduction? Imagine trying to find the main directions in a complex dataset, like spotting the brightest spots in a crowded room. That's what principal component analysis does, and singular value decomposition is its secret tool. When working with large datasets, reducing the number of variables helps make analysis faster and clearer. But how does SVD fit into this picture? Well, SVD breaks down a big data matrix into smaller, more manageable pieces. It takes the data and splits it into three parts: one that shows the main patterns, one that tells us how strong those patterns are, and another that points to the directions of these patterns. Think of it like taking a complex shape and finding its main axes. These axes are called principal components, and they show where the data varies the most. SVD helps identify these directions precisely. To do this, first, the data is adjusted so that each variable has a mean of 0. This step makes sure the analysis focuses on variation, not just the raw numbers. Then, SVD decomposes the data into three matrices. The right singular vectors, stored in one of these matrices, are the actual directions of maximum variance. The singular values tell us how much of the total variation each of these directions captures. By choosing only the top few singular values and their corresponding vectors, we can project the original data onto a smaller space. This process keeps the most important information while discarding less useful details. Unlike other methods that relying on calculating the covariance matrix, SVD offers a more stable and efficient way to perform this task, especially with large or sparse data. In machine learning, this technique simplifies complex data, making algorithms run faster and more accurately. For example, image processing tools like DALL-E or Midjourney use PCA to reduce the complexity of visual features, speeding up image generation. Productivity tools that analyze large text collections also use PCA to pick out key features, making data easier to interpret. But it's important to remember that reducing dimensions can sometimes hide important details. Practitioners need to balance simplification with preserving essential information, especially when models influence real-world decisions. So, in essence, SVD acts as the engine behind PCA, helping us find the main directions in data, cut down on unnecessary details, and make sense of complex information efficiently. This process is vital in many artificial intelligence applications, making data easier to handle and understand.